So now I'd like to talk about data cleaning. So this has a long history of fixing well-defined errors, where the objective is to fix or satisfy various key domain referential integrity constraints and also functional dependencies. And there's a recent excellent textbook called Data Cleaning by Ihab Ilyas and Sue Chu, which I encourage to read if interested. However, just focusing on the data doesn't necessarily guarantee the best model accuracy. And so I like to focus on that point. First, let me introduce one of the state-of-the-art data cleaning techniques to give a sense of how sophisticated these techniques have become. So this is Holoclean, where the idea is to repair data using probabilistic inference using three main ingredients. One is to satisfy integrity constraints. Another is using external dictionaries to check if some value is valid, and also using quantitative statistics altogether. So this table shows information about various people. So the columns are DBA name, AKA name, address, city, state, and zip code. And you can see here that there are various types of errors. So the one in the red is, if you just look at the data, you can see that if the AKA name is Johnnyos, then the DBA name is likely to be John Sr. So this can be repaired with statistics. Now, there's also a typo of Chicago here, and this can be repaired with a functional dependency, a zip code to city and state. Finally, you have these zip codes here in the middle, right? These are apparently invalid zip codes, and they can be repaired with external address listings. So the main point here is that there can be various data errors, and so there's no one technique that fixes them all. You need to employ multiple solutions altogether and in a probabilistic fashion so that most of them are satisfied as much as possible. Now, recently, some people have raised the question, does data cleaning improve model accuracy? Now, one stance is that if you perfectly clean the data, it's going to be most useful for model training as well. Now, I think the problem is that it's very hard to perfectly clean the data. And so then you have to think of a way to tailor for machine learning. So CleanML is a framework where the authors decided to evaluate various data cleaning techniques and seeing if they really help model accuracy. And so they used 13 real data sets, Airbnb citation and so on. And they considered 5 common error types: missing values, outliers, duplicates, inconsistencies, and mislabels. And 7 machine learning models: a decision tree, a random forest, AdaBoost, XGBoost, and naive Bayes. So without going into all the details, here are the key insights. The first, data cleaning does not necessarily improve downstream machine learning models. And in fact, in some cases, it can have a negative effect on these models. But luckily, by selecting a good machine learning model, we can eliminate the negative effects of data cleaning. Also, there's no single cleaning algorithm that performs the best, and one must choose adaptively given some error type. And so the takeaway message is that there's no one cleaning solution for all data errors, and you need to choose the right cleaning algorithm as well as the model that's intuitively compatible with that cleaning algorithm. So it is a difficult task, and it does require lots of work to get right. So recently, there have been data cleaning techniques that are more tailored for machine learning purposes. Active learning is one of the early works that's most popular. So this system iteratively cleans samples of dirty data and updates the model. So in this diagram, you have this sampler that chooses a sample that's likely to be dirty. And you can use data quality rules to identify such samples. The reason you have to sample data is because cleaning the entire data is presumed to be very expensive. And so then there's this cleaner that cleans the sample, maybe some oracle or person, and then the updater updates the model to be more accurate and also chooses the next sample. Now, this work has theoretical guarantees. So at some point, you're training your model on the clean sample plus previously clean data. So at some point, the model has obtains optimal accuracy as if it was trained on clean data only. But it does assume convex loss models like SVM. And also, the data cleaning is assumed to be perfect by some oracle. So these are two assumptions that may not hold in other applications. So for example, you cannot use this technique in a deep learning setting and get the same theoretical guarantees. But it's nonetheless very good to know about that this kind of technique exists. There's another technique that focuses on cleaning the label in addition to the data. So TARS is a system that predicts model accuracy out of noisy labels that are produced from crowdsourcing. So remember, data labeling is extremely important and you want to really improve the quality of labels to improve your model accuracy. So what TARS does is it chooses labels that are likely to be flipped, that are, have a low confidence because they were labeled by some incompetent workers. And then it also estimates how much the model is going to improve if this label is flipped after cleaning. So on the left-hand side, you see these examples, X1, X2, X3, that have labels that are crowdsourced, but there's also this probability that indicates the confidence you have of these crowdsourced labels. And the way you compute these values is you use a confusion matrix per worker. So you're assumed to have a history of how good this worker performed in the past. And so you're able to see the false positive rate, false negative rate, a true positive, true negative rates. So using that, you can compute probabilistically these probabilities. And so the higher this probability, the more confident you are in this label. So this means the less likely this label is going to flip. So 1 minus p means that this can be viewed as a probability of being flipped. And then there's an estimation of the accuracy of the model when the label is flipped. And you can subtract that by the estimated accuracy of the current model. And this can be used to determine whether this label is worth examining, such that if it's flipped, it actually is expected to help improve model accuracy. And so I'm not going to go into the details of how to estimate these three things, but the main contribution of the TARS system is proposing a way to make these estimations using these confusion matrices of workers. So that was data cleaning for ML. Now, I'd like to move on to the data poisoning topic, where compared to dirty data, poisoning has this malicious intent of making models fail. And so this is becoming an increasingly serious problem, mainly because data is now easier to publish through tools like Google Dataset Search. Remember, a dataset owner just needs to post metadata to the public, which will be automatically crawled by Google Dataset Search. And so someone can simply harvest that data using web crawlers without knowing that the data is poisoned. So this is a problem that's just waiting to occur. Now, the basic type of data poisoning is called label flipping, and where you simply flip labels from 0 to 1 or 1 to 0. But more recently, the data poisoning techniques have become much more sophisticated and therefore harder to defend against. So I just want to give an illustration of one of the state-of-the-art data poisoning techniques. So just to explain that, this is what we have to deal with. So data poisoning, this is a technique for deep learning. And one of the challenges in deep learning is it's very hard to know what kind of model is being used for training. And so the solution for poisoning is to use transferable poisoning attacks, which can still succeed without accessing the victim's model. So the idea is to train a substitute model, which is a model that we think is similar to the victim's model, but not necessarily the same, on the same training set. And so the assumption is that any attack that works on this model is also going to work on the victim's model. Now, a naive approach is to just add data poisoning as much as possible. And here's one of the baselines that the paper, this work considers. So the dark shapes here, the circles and the squares, are training data. And there is a target data that only exists in the test data, not the training data, that we want to make sure the attacker wants to make sure the model misclassifies. So we know this target. So the idea is to generate data poisoning around this target. So these are the two circles here. Now, this kind of attack doesn't necessarily work well in practice because it does shift the decision boundary to the right, but it doesn't shift it enough so that the target is misclassified. So the proposal of this work is to use a convex polytope attack where the poisoning forms this convex, and you want to make sure that the target is within this convex polytope. So then there's a higher chance that the decision boundary will really shift enough so that the model will misclassify the target later on. So how do we defend against data poisoning? Well, the task of data sanitization is to clean data and remove adversarial data poisoning. So let's say, before the attack, we have this classifier that correctly classifies the circles versus the squares. Now, after someone introduces these data poisonings, then the model is confused and the decision boundary totally changes. Now, after sanitization, hopefully we were able to identify these outliers and discard them. Then the model performs well as usual. So that's what we want to do. Now, there's been a lot of sanitization techniques proposed throughout the years. And recently there was a study of evaluating all of these defenses by developing attacks and seeing if the defenses worked or not. So this is just like the clean ML work where you want, this is an extensive evaluation on data sanitization. So I'm gonna just briefly describe some of the standard defenses used here. So L2 is removing points that are far away from class centroids using L2 distance. A slab is to project points on a line between centroids and then remove points that are far away from them, the centroids. A loss is to discard points that are not well fit by a model that's trained on the entire data set, and so on and so forth. Unfortunately, the conclusion is that no technique can adequately defend against carefully designed attacks. So here are some attacks that break all of these defenses. So influence attack concentrates all attacks on a few points instead of diffusing attacks. KKT attack finds poison points such that training on them yield decoy parameters, which are parameters that have a high test error but low training error. So they cannot be detected by the defenses. So I think that there's going to be no end in terms of data poisoning techniques advancing and defenses that try to defend against them. there's also always going to be some this back and forth. So in summary, data cleaning has been heavily studied, but not all of them are directly useful for machine learning. So more recently, there are data cleaning techniques that are tailored for machine learning purposes. Now, data sanitization is a similar problem, but has a different purpose of defending against poison attacks. Unfortunately, no sanitization technique can defend against all possible attacks. And this issue needs to be more studied in the data management community.